Welcome to Water Supply and Wastewater Engineering class. So today we'll be discussing lecture number 11, Rapid Sand Filter. So this is where unit 3, that is unit processes in the municipal water treatment. So in this unit 3 basically we are doing actually the water treatment, means step by step water is passing from one chamber to another chamber and it gets treated. So in the lecture number 10 we have introduced the filtration. So after let me set the context here for this lecture. So we already seen that water is from the source of water is coming to our water treatment plant. Then in the water treatment plant we have the first unit, that is screening, right? So after we screen all the floating objects present in the water, so after the screening water will go to next chamber, we call it aeration tank. So after aeration tank water will go to primary sedimentation tank. So after primary sedimentation tank, water will go to coagulation and flocculation tank where the chemicals is mixed into the water. So after coagulation and flocculation, water will go to next step, that is secondary sedimentation. So here you have the secondary sedimentation. So after secondary sedimentation, all the suspended particles will be removed in the secondary sedimentation. So after secondary sedimentation, water will go to next step, which we call it filtration. So in the filtration, basically the fine particle which is still present in the water even after the secondary sedimentation will be removed, and also the bacteria's virus present in the water, that also partially will be removed in the filtration step. So we are in the lecture 10, we have introduced the filtration, we have seen the philosophies of filtration, and we have seen the different types of filtration as well. Like we have seen two types of filters are there, right? The rapid sand filter and the slow sand filter. We have seen one more type, that is multimedia sand filter also we have seen, multimedia filter also we have seen. So in this lecture number 11, we'll be discussing about the rapid sand filter. So in that three types of sand filter, rapid sand filter is widely used for the municipal supply water supply treatment, because in the slow sand filter we have seen that it takes longer time, because the granular sand, that sand particle, the dimension will be very less in the slow sand filter. That's why water takes more time to travel into the filter medium, and the less quantity of filter has been filtered out, less quantity of water has been filtered out after in the slow sand filter. Whereas in the rapid sand filter, or the dimension of the sand particle will be little larger, so that the pore also will be more in the rapid sand filter, and the filtering capacity also will be increased. That's why in the city, like in the municipal water treatment plant, we use rapid sand filter, because the water demand is very high in the municipality. So in this lecture number 11, we'll be going through the entire rapid sand filter. We'll see what is the dimension, how to find it out, the designs, right? And then lastly we'll try to solve one problem also using the rapid sand filter. So let's get started. So after rapid sand filter, basically water will go to next last step, that is the disinfection. So in the lecture number 12, we'll be discussing about the last step in the water treatment plant, that is the disinfection. Means in this water, in the sand filter or the rapid sand filter, basically those suspended particles also will be removed, and some bacteria also will be removed, but still some other pathogenic bacteria will be present in the water, that will be removed in the last step, that is the uh, disinfection step. So let's get started with rapid sand filter design. So this is the diagram, typical flow diagram you can see in the rapid sand filter. So you have, here is the inlet of water. Inlet means here water is coming from the secondary sedimentation tank. So in this water, the small quantity of suspended particles, fine suspended particles will be present in the water. Also the pathogenic bacteria is also will be present in the water. So this water, so this chamber here, so everywhere in 1 2 3 4, you see these are valves, right? These valves will be open and closed depending on which operation we are doing. So currently we are filtering the water, so that means the valve 1 will be open, so the water will come from the secondary sedimentation tank. It will be filling this inlet chamber, and this valve number 4 is closed now, so water will be going into this chamber. So here you see exactly we have this filter, means we have the sand bed at the top, and then bottom at the you have the gravels. So water will pass through, so inlet water will come here, it will fill here, it will, so water will be coming here, and then the dimension of the sand particle will be larger compared to the slow sand filter, right? So the schematic diagram of sand filter also will be exactly same, but the only difference is the dimension of the sand particle. Here in the rapid sand filter, the dimension of sand particle is larger, larger, right? Larger dimension of sand particle will be there, and then at the bottom you have the gravels. Now water will be coming here, and because the dimension is more, so water will simply quickly pass through in the filter medium, that is through the different sand layers. After that, the gravel layers also will be there. So all the suspended particles which are present in the water will be simply filtered out in this step, and at the bottom basically you have this perforated pipe will be there, right? We call it laterals. So in that lateral, this type of holes will be there, the pipes. So through these holes the water will be entered into this main pipe, and it will be ultimately the clean water will be ultimately deposited at the somewhere at the tank. So next, from here water will go to next system that is disinfection. So that is the actual flow chart of the rapid sand filter. So now you can see how water is going from inlet to outlet. So now in the last lecture we have discussed about the backwater wash of rapid sand filter, because after 1 week or maybe after filtration, basically what will happen, the impurities will be simply filled these pores in the sand bed. So we have to clean the sand bed repeatedly, means every day or maybe every week, alternative days or maybe alternative days we have to clean the sand bed. So how we are cleaning, basically we are using the backwash of water. So what we do from so here actually we apply now clean water. So clean water we apply, and this bulb, all these two bulbs also will be closed. So this bulb number 3 will be open. So what will be there, so in the backwater cleaning purpose, we'll send the clean water in this area from this pipe basically, and water will be coming here, and it will simply, so here water will go to into opposite direction, from bottom to up it will go. So whatever dirt or the pollutants are present in this filter medium, it will simply go up, right? And then through this type of system will be there, where all the darts will be now suspended into the water. So water will be now then taken out into this wash water. So in that, now this water will be simply passing through, this bulb also will be closed during the washing time, and this entire water will be simply go, and this bulb 4 will be open. So the pollutant water will be simply going out, and it will be deposited here. So that's how the cleaning purpose, this cleaning purpose we call it back wash of water, right? Using this backwash, basically we are cleaning the filtering medium. So that's why the name also. And this filtering cleaning is done very frequently, means maybe either every day or every alternative day or weekly basis we are cleaning this rapid sand filter. So this is the actual filter mechanism of the rapid sand filter. So now if you see, this is the isometric view of rapid sand filter. So this figure you can see, basically you have the inlet means where the water is going. So this is the rapid sand filter. So here in this diagram it is shown two rapid sand filter. This is one rapid sand filter, this is another rapid sand filter, right? So and then you have this sand bed. So if you see, this is the cross sectional view. So at the top basically you have this two layer. First one is the sand layer, and the bottom you have the gravel layer, and then at the bottom even you have this piping system. So this is very much important. You have to understand very sincerely of what happens. So this is at the top is the water, that is water has to be treated, right? So gradually water will simply percolate through the sand bed and then the gravel bed, and then through water will be coming here, right? So here you have this pipes laid down. So these pipes we call it laterals. So these laterals will have holes. So small holes will be there in this pipe. So let me draw it here. So this each lateral will have this type of holes. I mean, these are the pipes, basically cast iron pipes, where these holes will be there. So through these holes basically water will be collected through these laterals, and all laterals are connected into the main pipe. So this is the main pipe we call it, right? So ultimately whatever water will be collected through these laterals, it will be deposited into the main pipe, and ultimately you will get the clean water in this direction. So in the rapid sand filter design, so as far as civil engineering is concerned, we have to design the entire rapid sand filter. So what are the things we have to design? First we have to design what is the dimension of the tank, right? So it dimension, breadth, weight, and the depth. So all these three parameters you have to design. This is first thing. Next you have to design what is the thickness of the sand layer, thickness of the gravel layer, right? And then you have to design how much space you have to keep for the sand to the top of this water tank. Then at the bottom again we have to design what is the dimension of this pipes, means what is the diameter of this pipe, what is the spacing of this pipe, what is the dimension of these holes, what is the diameter of this hole, what will be the spacing of this each hole, then what will be the diameter of this main pipe, how many laterals you are keeping it on this side, how many laterals will be keeping it in that side. So all these parameters you have to specify, and this type of drawing we have to make it for each water treatment plant. So by looking into this drawing now, in the site civil engineer will exactly plan or exactly construct the same structure into the water treatment plant. So now you understand how the different parts of water rapid sand filter looks like. So again, I am quickly explaining to you that initially you have this is the entire water treatment. This is the rapid sand filter where different layers are there. So first layer, if you see, this is the uh, filter, that is the sand filter at the top, and then at the bottom this is the gravel part, right? So now water will be coming into this top of this rapid sand filter, and then slowly water will be percolated through the sand layer and ultimately through the gravel layer, and it will be deposited at the bottom. So in this bottom you have this lateral pipes. In that lateral pipes you have these holes. So through these holes basically clean water will be coming into this each lateral, and each lateral will be again connected into this main pipe. So all the laterals, if you see, are connected into this main pipe, and through this main pipe basically clean water will be collected in this step. So this is the actual cross-sectional view of the rapid sand filter. So at the end basically we'll be solving one rapid sand filter design. So in that you will see all these parameters what I have explained here will be designed, like what is the dimension of this rapid sand filter, also what is the dimension of sand layer, then gravel layer, dimension of this laterals, like what is the diameter of this pipe, main pipe, lateral pipe, what is the hole diameter, what is the spacing, all these parameters will be designing at the uh, end of this lecture. So now the clean water head loss. Now you see, let me draw it here again. So this is the rapid sand filter. So you have different layers, right? Sand layer, and bottom you have the gravel layer, and here you have sand layer, and here you have the water which needs to be treated. So this water will be percolated through these two layers and ultimately uh, deposited into the clean water, right? So now the clean water head loss. So there will be head loss. Head loss means at the top you have the high head of water, but when the water percolates through each layer, the head loss will be happening, right? So the output or the effluent water will have, head loss will be there. So how much is the head loss at the effluent? That will be calculated using this formula. So many formulas are available, but most commonly we use Kerman-Cajonis equations. You can see these are the equations we use, right? And each parameter, these equation is basically empirical in nature, because by many trial and error and also some analytical model has been used to derive this type of equation. So in this course we are not deriving the codes, but we will be considering those equations for our calculation. So all the parameters, what is h is the head loss in meter, means head loss means water head loss will be happening from top to bottom, right? That is the head loss. So f is the friction coefficient. So now you see different layers, like you have the top, you have sand layer, then you have the gravel layer, right? So each layer water will be passing through the pores, so the friction coefficient will be f. Then the alpha is the porosity, means water is passing from each layer, right? So this is the porosity you have studied in the soil mechanics course, what is porosity. Then you have the phi is the particle shape factor, right? So we are discussing, we have seen, right, this what is the shape of this sand particle and the gravel particle also. So that comes from the phi shape factor. So L is the depth of the filter bed. So length of the filter, what is the length? D is the grain size dimension. Vh is the superficial filter velocity, like what is the velocity in which water is going out, effluent velocity. G is the gravitation due to space, due to gravity, we know 9.81. P is the fraction of particle within the adjacent ship size. Dg is the geometric mean. So Ng is the Reynolds number, and mu is the viscosity of this fluid. So viscosity of the water also we know. So all these parameters once we know, we can easily compute what is the value of head loss h. Okay, so using this formula basically we can compute what is the head loss, because head loss we have to monitor it, because head loss will tell you many more important parameters inside the filter media what is going on. So at the beginning, like you clean the filter, repeat send filter. Now you send the new fresh batch of water at the top. Now what will happen? So initially the filter medium in that, pore will be there, right? Because two sand particle in middle you have the pore. So initially the pore will be large, so the water will very quickly passing through the filter medium, and the head loss will be less initially. But as long as the water is still passing, and the pollutants present in the water will be simply filling those pores which is present in the sandbed. So when the pore is filled up by with the solid particles, then the head loss will be more at the bottom, because the very less water will be percolated through this filter medium, right? So the head loss will be very high. So in that case, by observing the head loss, you can understand that how much is the filter media has jam. You have to filter it out, you have to clean the filter medium. So depending on if more number of head loss is happening, then you have to clean the filter rapids and filter. So we'll be seeing in subsequent lectures also how head loss will be used for cleaning the filter media. So now, as I mentioned, to clean the rapids and filter, we use backwashing. So what is backwashing? Like from backside, basically we will supply the water, clean water, and this pollutant which is present in the water will be filtered out into the backwashing. So backwashing is basically done weekly basis or maybe even daily basis, so depending on our requirements. So for a filter to operate efficiently, it must be cleaned before next filter run, right? If the water applied to a filter is very good quality, then the filter runs can be long, right? If the filter quality is very good, then maybe weekly once you can clean it. But some filter can operate, that's what, some filter can operate even more than 1 week also. After 1 week you need to do backwashing, right? However, this is not recommended as long as filter runs can cause the filter media to pack down, so that it is difficult to expand the bed during the backwashing. Okay, that's why it is better that frequently you clean the water, maybe daily once, daily half an hour you keep it for the backwashing of filter medium. Now treated water is basically used for the backwashing, because backwashing, so whatever treated water we have deposited, we have collected from there, with this few quantity of clean water are used for the backwash cycle, right? Now the filter backwash rate has to be great enough to expand, because what happens is the particle is present in the filter medium, right? The pollutant will be deposited in the filter medium. So backwater also we have to send the clean water at a very high speed, so that the which particles which is present in the sandbed, that will be simply suspended, and ultimately it will be deposited into, it will be cleaned off. So that is the backwater, backwashing of repeat sand filter. You have seen now what is the working mechanism is going on inside. So now when backwashing is really needed, so that's what we have to monitor, the head loss of water. How much water is head loss is taken place, that you have to monitor. So initially the head loss, so this is the graph you see, this is the time versus the head loss. So initially the head loss will be very less, but as time goes, head loss will be increasing gradually, and after certain point, basically when you see the acceptable head loss limit, you reached it, in that case you just discontinue and you close the operations and you perform the backwashing. So the filter should be backwashed when the following conditions are met. So there are three conditions you have to meet it. The first one is the head loss, right, as I mentioned. So first one, so when head loss is reaching to some acceptable limit, you have to do the backwashing at this point. Next one is the flock starts to break even though through the filter, and the turbidity of the filter effluent increases. Like so after what happens is the flock which is present into the uh, sandbed, if after some time this flock starts breaking, so in that case again the effluent, whatever clean water, it will have more turbidity, right? So in that case also, in that position also, you have to immediately stop the washing, and you have to use the back washing. And a filter runs reaches to the given hour of operation, like if 24 hour if you complete, or maybe 1 week, or depending on the design of filter medium, right? When it reaches end of this time, then you have to do the filtering of backwashing. So next we'll be discussing about the operations troubles in the rapid gravity filter. Okay, so you have now understand what is gravity filter, the rapid sand filter. Basically, water is passing through different sand layer, as well as at the bottom you have the gravel layer, and ultimately it deposits at the bottom. So you will you will find on a field few operational troubles with this rapid gravity filter. So first problem you will find is the air binding in the sand filter. What is air binding sand filter? So when the new filter is newly commissioned, basically the loss of head will be less, right? Because at the beginning, the head loss we have discussed, it will be very less, generally very small. However, the loss of head goes increasing as more and more impurities are trapped into it, right? As long as these pores in a sand are filled up with these impurities, so the head loss will be more, right? So that stage is finally reached when the frictional resistance offered by the filter medium exceeds the static head of water above the bed, and most of this resistance is offered by the top 10 to 15 centimeter of sand layer, because 10 to top layer sand layer, basically the impurities initially will be stuck into this top layer, right? So that's why the top layer, all the pores will be filled up by these impurities, and ultimately the bottom sand acts like a vacuum, right? The bottom sand will be acting like a vacuum because there the pores are open, whereas the top layer the pores will be filled up because of impurities, right? And the water is stuck through the filter media, water will be stuck, and this negative pressure will be developed because at the bottom you have the suction, whereas at the top you have the high pressure. So this will create the negative pressure into the filter medium, okay, and this tends to release the dissolved air and other gases present in the water. So the formation of bubbles that takes place, which sticks into the soil sand grain, and this phenomenon is known as air binding, as the air binds with the filter medium and stops its functioning. Now you understand what is air binding. So let me draw it quickly here. So you have different layers, right? Initially you have the sand layer at the top, and you have the gravel layer at the bottom. So what will happen when the water passing through this filter medium, so that the top layer, all these pores will be filled up with the impurities, right, which is present in the water. That impurities will be simply stuck into the top few layers. So top few layers will be simply stuck, whereas bottom sand layer as well as the gravel layer, the pores are still open, right? So this will create a vacuum here, because here ports are open, whereas the top layer it is completely packed. Is not it? So that phenomenon will create a negative pressure. Negative pressure means now pressure will be high at the top, whereas bottom pressure is less, right? This negative pressure will create, and because of that, the air gas bubble which is present in the water, that will be simply going up, and this process we call it actually air binding. So this air will be simply binding, will be with this sand particle, and this ultimately stops the functioning of the, after some time basically water will be simply stuck at the top. The water won't percolate through the different layers, so it will be stop functioning. The entire filter medium will stop functioning. So this process is called basically air binding. So air binding you will find frequently on a rapid sand filter. So to avoid this type of air binding, so we have to clean this filtered medium frequently, every day or maybe every week, every alternative day we have to clean through backwashing. We have to clean, so that the no air binding air bubbles form inside the filter. So now the next problem you will find is the formation of mud ball. So the mud ball from the atmosphere, the mud from the atmosphere usually accommodates on the sand surface. Top layer basically it will form, and the dense layer basically it forms. So during this if you don't wash this sand bed, then what will happen? This mud which is deposited at the top, this will be, in a ball shape it will be forming, and this we call it actually mud ball. So that's why it is very much essential to clean this rapid set filter frequently, every day or every week we have to clean it out. Then another problem you will find is the cracking of filter. The fine sand coating contains the top layer of the filter bed shrinks and causes the development of cracks on a sand bed. With the use of filter, the loss of head and therefore pressure of the sand bed goes increasing, and thus the crack size also will increase. So you will find these cracks initially micro cracks at the top of this filter medium, and gradually the crack size will be increasing when the pressure is also increasing. So that also we have to take care. So these three primarily problems you will find it out on a rapid sand filter, and that appropriately you have to take care about this filter part, because here, so what is the solution for that? Basically we have to clean the filter medium very rapidly. So the remedial measurements to prevent the cracking of filter medium and formation of mud balls, basically what you have to do, breaking the top fine mud layer with rakes and wash off the particles. So very frequently we have to wash the filter medium, and also washing the filter with the solution of caustic soda we can use for the filtering the medium, and remove and clean and replace the damaged filter. Right? At the top portion of the sand layer, if you can replace it, every month or every week, so and you replace it with the new good quality of sand. So these are the methods for how you can overcome the trouble which we have seen. So now we understand what is actually the rapid sand filter. Now we'll see the actual design. The standard design practice of the rapid sand filter. So in the if you see at the second slide, I have seen the isometric view of the rapid sand filter. Here you have seen the what are the design parameters you have to design. So first one is the maximum length of the lateral. So which one is the lateral? Let me draw it here quickly. So at the bottom, so this is a tank where at the bottom you have this pipes, right? At the center, this is the main pipe, whereas these are the laterals. Now if you see the top view, uh, top view we will find you have a main pipe, and from the main pipe this type of small pipes are going out, right? These pipes we call it laterals. So lateral will have the holes on it. So these are the lateral pipe I'm talking. This structure you will find at the bottom here at this level. So at this level, this is the structure you will find. This is the lateral. So first you have to find out what is the maximum length of the lateral, right? What is the length of this lateral? So this normally the maximum length of lateral is not less than the 60 times of its diameter. 60 times of the diameter of this lateral, right? Then the spacing of holes, as I mentioned, this there will be a hole in the lateral. So this is hole. This type of holes will be there everywhere. So through these holes, basically the clean water will be collected, right? And ultimately it transfers to this main pipe, and from main pipe it will go to outside. So next step is basically spacing of holes. So what is the spacing of each hole? That normally it is 6 millimeter hole at 7.5 centimeter, or 13 at 15 to 15 centimeter. These are the standard values you can choose while designing the rapid sand filter. Then the cross-sectional area of lateral normally it is not less than 2 times of the area of the perforation, area of the hole basically. So cross section of the manifold we call it, this is this middle pipe, big pipe, we call it manifold. So this is the cross sectional view, and this is the top view. You can see this is the manifold. Okay, so the cross sectional area of the manifold is normally 2 times the area of the laterals. Then the maximum head loss is allowed 2 to 5 meters. So the head will be at this top, and the loss will be at the bottom, right? Head loss, the head difference between this inflow and outflow should be 2 to 5 meter in this range. Spacing of lateral 15 to 30. The spacing of this is one lateral, this is another lateral, right? This is the spacing. So this spacing normally you can keep it 15 to 30 centimeter. You can understand how much is the spacing. Now the pressure of the wash water at the perforation should not be not more than 1.05 kg per centimeter square. The velocity of flow in laterals should be 2 meter per second. So the velocity of flow inside each lateral, these are the standard values given in our Indian code. So while you are designing the rapid sand filter, you can choose the values from this table, and accordingly you can design it. So the velocity of flow in the manifold means this middle portion, right? Middle portion is 2.25 meter per second. You can consider velocity of flow in the wash water is in this range. Velocity of rising water in this range. Amount of wash water normally 0.2 to 0.4% of the filter water, right? So maybe every day how much quantity of water you are filtering out of which 0.2 to 0.4% you can reserve it for the washing of the water, washing of this rapid sand filter. Then you have the time of backwashing. The time of backwashing normally is 10 to 15 minutes. Every day you can keep 10 to 15 minutes for the backwashing purpose. So head of water above the filter normally 1.5 to 2.5 meter, whereas free boat is, if you see the cross section, then at the top layer you have the sand layer, right? So you have here you have the sand layer, and the bottom you have the gravel layer. So this is the gravel layer, and then you have the sand layer. So this portion, this free portion, we call it free boat. So free boat you can keep it 60 centimeters. So this height may be 60 centimeter. You can keep it. Then the bottom slope, we have to maintain the slope because water has to flow right through this manifold. So bottom slope 1:60 towards the manifold. We have to keep it right. So Q is the total how much quantity of water you know is coming out from the manifold. This is the formula you can use. Okay. So B is the breadth of this breadth of this repetition filter, and the height is the height, right? L is to B ratio 1.25 to 1 is to 33, you can consider it. So depending on, these are the standard values are given to us. So whenever you design a repetition filter, we can choose the values from this table or from this parameter, and we have to design it. So now we actually will be solving one problem, and we'll be using this formula, these values actually extensively. So let's get started. So now this is an actual real life problem. If you see, you have to design a rapid send filter to treat 10 million liter of raw water per day. So one day you have to treat 10 million liter of water, right? Allowing 0.5% filtered water for the backwashing. So as I mentioned, every day you have to backwash it, right? So every day half an hour is reserved for the backwashing, and 0.05%, 0.5% filtered water is used for the backwashing. So assume the necessary data. Any data you can assume it, and you have to design it. So design means you have to, as I mentioned, you have to find out what is the dimension of the filter bed, what is the dimension of the filter tank, what is the dimension of the lateral spacing, so spacing of holes, all these parameters you have to find it out. That is, we call it design. Okay, so now let's get started about the designing. So now first, what we understood, what is given in the question, that every day we have to clean 10 million liter of water, right? 10 million liter per day. One day we have to treat, and out of which 0.5% again will be reserved for the backwashing. Is not it? So every day now total how many liter of water we have to treat? So 10 million anyway we have to supply it for the household, and plus 0.5% is again required for the backwashing. So this plus 0.5% means 0.5 by 100, right? No, okay, so this comes out to be how much? So 10.05. So you have to treat every day 10.05 million liter of water. It's not it. 10 liter is, you have to 10 million liter you have to supply it into the household, whereas 0.05 meter, that much quantity of water, you have to reserve it for the backwashing. So every day half an hour is used for the backwashing. So the whatever filter medium we'll be designing, that will be running not 24 hour but 23.5 hour, right? Why? Because half an hour we are reserving for the backwasher. So every day half an hour is used for backwashing. So how much remaining? Remaining is 23.5 hours. So our filter will be running for 23.5 hour every day, and that, and total water has to be treated is 10.05. Why? 10 liter you have to supply, and 0.5% of water basically we have to keep it for the backwashing. Is not it? So total 10.05 liter of water we have to treat it every day in a 23.5 hour, not 24 hour. So now total filtered water, how much we have to filter it out? So 10.05 is the total. We have to filter it out. We are converting 10 to the power 6 means million liter into the liter. We multiply 10 to the power 6 divided by 23.5, because total 23.5 hour actually we are getting one day, right? For 30 minutes is reserved for the backwashing. So if you do it, you will get that much quantity of, that is 0.427 milliliter, million liter you have to treat per hour. So 1 hour that much water has to be treated. So the effluent speed will be that much, quantity will be that much of water. So let's rate of filtration, we consider it, because we are considering it is a rapid send filter, right? So we have seen for the rapid send filter, the filter rate is 3000 to 5000 liter per hour per meter square bed. So let's consider here that 5000. So whatever we'll be designing, that the output capacity will be 5000 liter per hour per meter square bed. So total how much quantity of water we have to, so the area of filter will be that much, is the total water we have to filter it out, and this is the time. And what is the filtering mean, like what is the filter rate, right? 1 by 5000. So that will be the area of the filter bed. So filter bed means, so let me, this is the tank, but this is the top layer, right? Top layer is sand layer, and then you have the second layer, that is the gravel layer. So this is the gravel layer, and then the bottom you have this pipe. This is the main fold, and you have the lateral. Both sides you have the lateral. Now if you take the top view will be something like that. You have the at the same bottom, you have the main pipe, and then you have the lateral. So all these things you have to design it. So these are the lateral pipe, right? So now area of this filter bed, so total area of this filter bed now we are computing. So already we assume that the rate of filtration is 5000 liter per hour per meter square bed, is not it? So total we have to filter it out, that much 10.05 into 10 to the power 6 liter divided by total time, how much you have, 23.5 hour, and the rate is 5000. So if you do it, then you will get area of filter, that is total area of this filter is 85.5 meter square. So 85.5 meter square is the total area of filter required. So now we will construct two filters. This is one filter, one more side, or two different filters will construct it. So then the each bed will have, so two bed will construct it, right? So total we need 85.5 meter square area filter bed. So we'll construct two bed as I mentioned. So that's why 85.5 divided by 2. So each bed dimension will be 42.77. So this is one bed, another same bed we have to construct it. So two bed we are constructing, and each bed dimension is 40, each bed cross sectional area is 42.77 meter square. So length by breadth ratio, you can take it in the last slide we have seen some standard value. So we'll be considering 1.3:1 is the length by breadth ratio for this filter medium. So just if you plug in both values, you will get it. And total area is 42.77, right? From there you easily compute what is the breadth. So breadth is 7.5 meter, whereas the depth of the breadth is breadth is 5.75, length is 7.5, and also the depth of sand layer you can assume 50 to 75 centimeter in this range, right? So now we have to design this under drain also, right? This laterals you have to design, as well as this manifold, that is main pipe also you have to design it. So now let's design the under drainage system. So total area of hole, so total area of hole means what? These holes are present in this each lateral pipes, right? Lateral pipe consists of these holes we have seen. So the total area of holes we can consider it 0.2 to 0.5% of the bed area. So bed area already we have computed it. It is 85.5. We divide it by 2 because two bed we are constructing. That is 42.77 is the one bed area, is not it? So 0.2 to 0.5% is the total bed area, is the total whole area we can consider. So if you consider 0.2%, then the total bed area is 42.77. So 0.2 by 100 into 42.77, this will give you that much is the total whole area, right? So this hole will be there in the lateral pipes, right? So total whole area is that much. So now area of lateral, so how much area of lateral, that also we have seen in the last slide, that we can consider 2 times the area of the whole of the lateral, holes of a lateral. So whole of a lateral we already computed 0.86. So if you multiply it by 2, you will get the area of lateral. And simply area of manifold will be 2 into area of lateral. So area of lateral, whatever you computed in this step, if you multiply it with 2, you will get the area of manifold. So the total area of manifold, manifold means this middle center pipe, that will be 4 into 4 times into the area of hole, right? 2 into 2, 4 times the area of hole. So area of hole already we have computed 0.87, 0.086. So this multiplied by 4, you will get what is the area of manifold. So area of manifold means this main pipe at the center, right? That much area, cross-sectional area is required. Then what will be the diameter? Easily we can compute it, right? Diameter will be pi by 4 into d square will be the area, is not it? This equal to pi by 4 into d square. If you do it, then from there you can find out what is the d square. D means diameter of this manifold. So d will be root square of 4 into cross-sectional area, is not it? So let me do it here quickly. So this is the cross-sectional area of this main pipe, is not it? So area, area is equal to simply pi by 4 into d square, right? So now we are finding out what is d. So d will be 4 into area by pi and root square, is not it? So that's what we have done it here. So from there easily you can compute what is the diameter of the manifold. So which comes out to be 66 meters. So 66 centimeter is the diameter of this manifold. So now assume the center to center distance of the lateral center to center distance is 30 centimeter. Then the total number, how many you can provide it? So total, what is the length? So length already we have computed, right? 7.5 centimeter total length of this bed. So each center to center distance already we have assumed 30 centimeter. Then how many lateral we can provide it? 7.5 divided by 0.3. 0.3 is center to center spacing. So now we got it 25. So 25 number of lateral we can provide. So this side 25 number of bars laterals we can provide, left side also we can provide 25 numbers. So total 50 lateral actually we can provide it in this bar. Now the length of the lateral will be, total breadth is how much? Total breadth we have already assumed B value is 5.75. So 5.75 is the total. So half will be the length of one lateral, is not it? So if you 5.75 divided by 2 minus, you have the manifold at the center, right? That's why we are minus 0.66 by 2. You will get, this is the length of the lateral, length of the one lateral, you got it. Now the cross-sectional area of the lateral, that also will be 2 into the area of perforation, right? 2 into area of the lateral, 2 into area of perforation or hole. So the hole diameter we consider, let's consider 13 centimeters. The hole will be there in the lateral. So that consider 13 millimeter. Small holes are there in the lateral. So from there easily you can find the number of holes. How many holes can you provide? That comes out to be 650 approximately. You can easily compute it, just and then you get total 650 holes are provided, number of holes. Okay, so now come, so number of holes already 650 and total 50 laterals you provided, right? 25 in the left side, 25 in the right side. So total, so each, so number of holes per lateral will be 13. So let me draw it here again. So you have, this is the cross sectional view, and at the center you have this main pipe, and then you have these laterals, right? So total 25 laterals are there in each side, and each lateral you have these holes. So this type of holes are there. So number of holes per lateral is 13, already we computed. So area of the perforated lateral. So total area is how much? So 13 into the area of each hole. So area of each hole is pi by 4 into d square, right? So that much. So now the spacing of hole already, how much you know. So total length is how much? Length of the lateral already we computed 2.5 divided by total 13 holes are there, right? So if you divide 13, so there will be the spacing of holes. See, now all the parameters gradually we are calculating one by one, right? So now the cross-sectional area of the lateral, cross-sectional area of the lateral is 2 times the area of the perforation of the lateral, right? So 2 times into area of the perforation is how much? 17.2724 into 2, that is the area of the lateral. So from there again pi by 4 into d square, from there you find out what is the diameter of the lateral pipes, which comes out to be 6.63 centimeter. That is the diameter of the each lateral pipes. Now you can check it. We, in the last slide we have seen, right, in the last slide, that this length of the lateral should be less than equal to 60d. So 60 into d is this much we computed, that comes out to be 3.98 meter, and which is more than the length of the lateral. Length of the lateral is 2.54, so it is acceptable, so that's fine, right? So now the rising water velocity is 50 centimeter per minute. We have considered it from the earlier chart. Now the wash water discharge per bed will be 0.5 by 60. By 60 means 1 hour, right? 1 hour will be by 60 minute into, this is the cross sectional area of the bed. That much is the water deposited in every second. 0.36 meter cube per second water is deposited, right? So velocity through the lateral. So how much, what is the velocity in the lateral? That will be total, how much water is deposited per second by the total cross sectional area. So by the cross sectional area already we know, from there you can find out what is the velocity. Similarly, velocity in the manifold also you can easily compute it, total that much divided by the cross sectional area of this manifold, you will get it what is the velocity there. So now all the parts we have designed it. So this design part is now completed. So now we'll be designing the wash water. So back we have to wash water, right? We have to backwash it. So for that we are doing the calculation now. So the discharge of wastewater, wash water per bed, if we consider 0.36 meter cube per second, and the size, basically we already computed this value, right? This one, and size of the bed already we know, this value also we computed. So assume 3 running and level wise, so total 3 steps if you consider, then each step will be this divided by 5.75 divided by 3, you will get 19 meter square. So at the top we are providing those wash water gutter. So assume B value is 0.03. From there, how much head loss is happening? This formula we have seen, right? So total, it will be each value will be 40 approximately. You can consider 40 centimeter plus freeboard. Freeboard means how much will be the top layer is vacant. So freeboard, which one? Let me draw it here. So this is the cross section, right? And initially you have the sand layer here, and the bottom you have this gravel layer, and this portion, this top portion, we call it freeboard. So freeboard, we consider it 5 centimeter, and 40 is the total height, right? Height of this total one. So 45 centimeter. So now clear water reservoir for the backwashing. So backwashing we have to reserve, right? Which is from the main water. So for the 4 hour capacity, so capacity of the tank will be how much for the 4 hour? That is uh, this is the dimension of this filter bed for 7.5 into 4.5 into 2, because 2 bed we have, right? 4 hour, and we are converting, so that much is the 4 hour, we are, that much is the capacity of the tank, right? So assume the depth d value is 5 meter, and the surface area, simply you can compute it, right? From there if you divide it by 5, then you will get it, that much is the surface area. So again, length by breadth, ratio we can consider it 2. From there is you compute b and l value, right? So all these values we have already considered in the earlier slide. We have shown one table, right? From there all the value we have considered. So the diameter of the inlet pipe will be 15 centimeter, and easily you can compute it, right? What is the velocity, diameter in the wastewater pipes, all these values, if you plug in, you will get these values. So for the 5 minute air required, easily you can compute that much air is required for the backwashing. Okay, because in the backwashing we are pushing the water from the top to bottom to top, right? We are cleaning the water, that much air is required to pump. So compressor values and all we have assumed it from the standard value, and we got it how much air. So like that, basically we can design the entire rapid send filter. You can see the entire part, all these things we have designed, like what is the dimension of columns, dimension of height, the dimension of this filter bed, right? And this dimension of this lateral, dimension of what is the spacing of this lateral, spacing of holes, all these parameters we have designed it, and we have completed the entire rapid send filter. So what I request you everyone, this try to solve this problem from basics, step by step. You do the calculations in your hand, and you complete this problem. Okay, so this concludes the rapid send filter design. Now in the next lecture we'll be discussing about the disinfection. Means after the water coming out from the filtration, water will go to last step, that is the disinfection. Thank you.